Hello students, I am Sachitrakar. Welcome to Cars Physics. This is my lecture 9 on electrostatics and we are continuing electric charge and electric field. In this lecture, we will discuss some numericals based on electric field. Of course, I have divided the total numericals into two lectures. In lecture 9 we will discuss some of the numericals based on electric field, and also in lecture 10 we will discuss some other numericals based on electric field, and the whole numericals are divided into two lectures in part 1 and part 2. Okay, let's start. Question number 1. I have already written two questions. Okay. Question number 1. A gold nucleus of atomic number 79 has radius 6.6 into 10 to the power minus 15 meter. Find electric field on the surface of nucleus. This is most basic and fundamental numericals on electric field due to a point charge. Okay, so gold nucleus, let's consider this is the gold nucleus, not too big. I have not seen gold nucleus, means it should be very small. Okay, and as we know, nucleus contains protons, means total positive charge is distributed throughout the nucleus, and we may assume the total positive charge due to the presence of protons are concentrated at the center of nucleus. So Q is total positive charge of nucleus, and this is radius of nucleus R. As it is given, we have to find electric field on the surface of nucleus. Okay. So here we have to find electric field on the surface. Okay. So this is the position of point charge and we have to find electric field on the surface. Okay. So here distance from the point charge is R, which is also radius of the nucleus, and as we know, magnitude of electric field due to a point charge is given as K Q divided by square of distance. Okay, then electric field K 1 divided by 4 pi epsilon naught, then total charge of nucleus is product of atomic number and charge of electron divided by square of distance. 1 divided by 4 pi epsilon naught is 9 into 10 to the power 9 in M case, and atomic number is 79 in charge of electron 1.6 into 10 to the power minus 19 coulomb divided by square of distance, means square of radius. It's given 6.6 into 10 to the power minus 15 meter square, and solving it we will get magnitude of electric field on the surface of gold nucleus. We will get 26.1 into 10 to the power 20 Newton per coulomb. So this is magnitude of electric field. Again, to know direction, as we know, electric field intensity is defined as force experienced by unit positive charge. Okay, thus magnitude and direction of electric field intensity due to a point charge is same as that of magnitude and direction of force experienced by unit positive charge. Okay, then direction of field intensity is along the direction of force experienced by unit positive charge. Let's place our unit positive charge to know the direction of electric field. This is positive charge of nucleus, means this is the point charge due to nucleus, positive charge of nucleus, and this is unit positive charge. Obviously this positive charge will repel it. Then direction of force is outward, and direction of field intensity is also radially outward direction, as we have discussed in previous lectures. Okay, this is fundamental question on electric field due to a point charge. Can I erase it? Okay. Question number 2. In question number 2, 2 point charges of 4 microcoulomb and 16 microcoulomb are separated by a distance of 30 centimeter and it is asked to calculate a point along the line joining the 2-point charges where electric field intensity is 0. Okay, before discussing the question, let's analyze some similar form of questions. Okay, let's consider these are positions of 2-point charges, and 2-point charges are respectively plus q1 and plus q2. Means both the point charges are similar nature of positive and positive. Let distance between them is L. Of course, we may consider another identical question. Let this is minus q1, this is minus q2. In both cases, magnitude of q1, let magnitude of q1 is greater than that of magnitude of q2, and here also distance between 2-point charges is L. See students, I am discussing about 2-point charges separated by a distance L, but 2-point charges are similar, means positive positive or negative negative. So we have to find a point along the line joining the 2-point charges where electric field intensity will be 0. Since there are 2-point charges in both the cases, so electric field due to 2-point charges will be at a point, means if you consider any point along the line joining the two charges, there will be two field intensities due to 2-point charges, and to have 0 resultant field intensity, we have to get magnitude of resultant field intensity 0. Okay, let field intensity due to q1, let E1, field intensity due to q2 is E2. To have 0 resultant field intensity, we have to take vector sum of electric field intensity due to the 2-point charges as per superposition principle of electric field intensity. Okay, then to have 0 resultant field intensity, sum of two field intensity should be 0, means E1 is equal to minus E2. It means magnitude of E1 must be equals to magnitude of E2. Again, negative sign implies that they should be opposite in nature. As per principle of vector addition, if resultant of two vectors is 0, then two vectors must have equal in magnitude and opposite in direction. Here also the similar thought. Electric field due to 2-point charges must add up to give 0 resultant. To have it, two field intensities due to 2-point charges must be equal in magnitude and opposite in direction. Okay, if both the charges are either positive or both the charges are negative, then we have to find a point along the line joining the 2-point charges where resultant electric field intensity is 0. In this case, the simple trick, the point must be in between the charges. Okay, in between the charges, if both the charges are either positive or both the charges are negative. Okay, so if both charges are of similar nature, then the point where resultant field intensity is 0 along the line joining the two charges must be in between the two charges. How? Let's consider this point where resultant field intensity is 0. Again, as per principle, where we have to find electric field intensity, we have to place an unit positive charge at that point, since electric field intensity is force per unit positive charge. Okay, force experienced by unit positive charge is equal to electric field intensity. That's where we have to find electric field intensity. The first principle is we have to place an unit positive charge. Okay, let this distance from plus q1 is x and remaining distance from plus q2 is L minus x. See students, as per our general thought, similar charges repel and dissimilar charges attract each other. This is positive, this is positive. So q1 repels unit positive charge. Let field intensity due to plus q1 is E1. Similarly, plus q2 repels unit positive charge, let this intensity is E2. We have got one condition, we have satisfied one condition, means the two intensities must be opposite in direction. Then next condition, two intensities must have same magnitude. Okay, let's analyze second case. Again take a point here at a distance x from minus q1 and at a distance L minus x from minus q2. Let's place here unit positive charge, then minus q1 will attract unit positive charge. Let intensity is E1, minus q2 will attract unit positive charge. Let intensity is E2. Okay. To have zero resultant field intensity, the component field intensities E1 and E2 must be must be opposite in direction and must have equal magnitude. In both cases, we have got opposite in direction. Thus, it is very clear that if 2 point charges are either positive or negative, then the point along the line joining the two charges must be in between the charges. This is the point, and in between the charges, this is the point. Okay. Then where should the point should be taken? The principle, you should keep it in mind. The point should be nearer to the smaller charge. Sorry, I am taking now Q1 is less than Q2. Then Q1 is smaller in magnitude and Q2 is greater in magnitude. Then the point should be closer to smaller charge. Why? Why? Magnitude of electric, we have got already directions are opposite. Magnitude of electric field intensity is KQ divided by square of distance, and this shows magnitude of electric field intensity directly proportional to magnitude of charge and inversely proportional to square of distance between them. Okay. If magnitude of charge is more, then electric field is more. If distance is more, then electric field is less. Okay. Considering smaller charge, for smaller charge, these are the concepts for smaller charge. Charge is less means Q1 is less than Q2. Thus, electric field means magnitude of electric field for smaller charge is smaller. But distance from smaller charge is less means magnitude of field will be more. Okay. So for smaller charge, electric field, magnitude of electric field is smaller due to magnitude of charge. Okay. And magnitude of electric field is greater due to distance from the charge. Okay. Thus, for smaller charge, since magnitude of charge is smaller, electric field directly proportional to magnitude of charge, magnitude of electric field will be smaller, but we have taken the point at a smaller distance from the smaller charge. If distance is smaller, then electric field will be greater. And accordingly, we may compare this point for greater charge means for bigger charge. If magnitude of charge is more, then electric field will be more. Magnitude of electric field will be more. But distance from greater charge is greater. So distance is greater, so electric field will be smaller. Okay. We need a balance point along the line at any point. Okay. So as to have magnitude of field intensity due to 2 point charges at a given point will be same. Thus, from one discussion means considering only smaller charge, we can have idea on larger charge. For larger charge, electric field is larger due to magnitude of charge. For larger charge, electric field will be smaller due to larger distance. For which, if 2 point charges are given, we have to get zero resultant field along the line joining the charges. Again, I am repeating my sentence. If 2 point charges of equal nature, positive positive or negative negative, we have to take a point along the line joining the charges in between the charges, between q1 and q2, between q1 and q2. These are the points, number 1. Number 2, the points should be taken nearer to the charge of smaller magnitude. Okay, then here directions are opposite. The only condition is magnitude of E1 must be equals to magnitude of Q2, means magnitude of electric field due to plus Q1 must be equals to magnitude of electric field due to plus Q2, or in case of minus Q1 and minus Q2, these two are similar range of questions. Okay, then electric field due to Q1, magnitude of electric field Q1 divided by square of distance. Distance from smaller charge is x to the point where we are assuming that electric field intensity is 0. Then this must be equals to magnitude of electric field due to the charge Q2. Distance from Q2 is L minus x. Then distance is L minus x square. For both the type of questions, the same concept and same formula. Okay, now we'll return to our question number 2. Okay, 2-point charges 4 microcoulomb and 16 microcoulomb, both are positive. Then Q1 is 4 microcoulomb and Q2 is 16 microcoulomb, separated by a distance of 30 centimeter, means L is equal to 30 centimeter. So we may do this of R. If the charges were negative, we may consider this diagram, any of diagram. Okay, let electric field is 0, resulting electric field is 0 at a distance x from Q1. Then as per this principle, Q1 is 4 microcoulomb divided by square of distance is x, is equal to Q2 is 16 microcoulomb. Then distance from Q2 is L minus x, but here L is 30 centimeter, minus x whole square, k get cancelled, microcoulomb get cancelled, 4 by x square is equal to 16 divided by 30 minus x whole square, taking square root on both sides, 2 by x is equal to 4 divided by 30 minus x. Now cross multiplying, 60 minus 2x is equal to 4x, and solving we will get 6x is equal to 60 centimeter and x is equal to 10 centimeter. Thus, in this question, we can get 0 resultant field intensity at a distance 10 centimeter from smaller charge, means from plus 4 microcoulomb. Or if the charges were negative, then we may say from minus 4 microcoulomb. Okay. So this is question number 2. Then question number 3, I am erasing, and I hope you are taking screenshot, or you may see repeatedly. All these are fundamental questions, nothing big thing. I will promise you, the only thing I will promise you that I will try to touch all the concepts, means some basic concepts while approaching the numericals. Okay, and your concept will be clarified. Okay, that's my motto. Okay, don't miss lecture 10, in which some other numericals on electric field will be discussed. Don't miss. Okay, then I am changing this question. This is question number 3. Okay, 2-point charges, I am changing the datas a little bit. 2-point charges of plus 16 microcoulomb and minus 9 microcoulomb are separated by a distance, let 8 centimeter. See, this is the different case. In previous question, we are discussing either 2 charges both are positive or both are negative, but here one is positive, other is negative. Okay, let this is Q1 plus 16 microcoulomb, this is Q2 minus 9 microcoulomb, and distance between them is 8 centimeter. Okay, Let's first analyze the concept. Suppose this charge is positive plus q1, this charge is negative minus q2, and distance between them is L. We have to find a point along the line joining the two point charges where resultant electric field intensity is 0. Can we take a point along the line joining the two charges, means in between the two charges? Let's see. Okay, let's consider a point q2 is smaller, okay, distance from the smaller charge, okay, nearer to smaller charge, let this distance is x, okay, the remaining distance is L minus x. Let's assume that at this point resultant field intensity is 0. Again, where we have to find electric field intensity, we have to place an unit positive charge. Let's place an unit positive charge, okay. Plus q1 will repel it, let intensity is E1. Minus q2 will attract unit positive charge, let field intensity is E2. What happened? Here E1 and E2 are in same direction, okay. E1 and E2, electric field due to plus q1 and electric field due to minus q2. Plus q1 repels, minus q2 attracts, and both the field intensities are in same direction, okay. But to have 0 resultant intensity, the basic condition, if two vectors add up to give 0 resultant, the basic condition is two vectors must be opposite in direction. So here, since angle between E1 and E2, if opposite in direction, then angle will be 180 degree, okay. They are in same direction, so angle between them is how much? 0 degree. So if angle between two vectors is 0 degree, then magnitude of their resultant will be equals to sum of magnitude of the vectors, okay. So here we can't get 0 resultant field intensity in between the 2 point charges along the line joining the charges, okay. I'm erasing. So where we will get a point where resultant field intensity due to these charges will be 0. This is the line joining the two charges. Again the same concept. The point where resultant field intensity due to these 2 point charges will be 0 should be nearer to smaller charge, means nearer to the charge which has smaller magnitude. Here q2 has smaller magnitude. Let's place an unit positive charge at this point, means here we have placed unit positive charge at a distance x from the smaller charge. Now see, plus q1 will repel this unit positive charge, let field intensity due to plus q1 is E1, and minus q2 will attract it, let field intensity is E2. Then basic condition is satisfied. Two intensities are opposite in direction. To get 0 resultant by adding two vectors, the two vectors must be opposite in direction and must have equal in magnitude, okay. Then electric field intensity due to q1 is E1, magnitude of q1 E1. Then this is equals to k q1 divided by square of distance from plus q1 to this point is L plus x whole square. And similarly, magnitude of field intensity due to minus q2, which is attracting, then this is equals to k q2 divided by square of distance from minus q2 is x square. They are already oppositely directed. Then only condition, as we have discussed, magnitude of E1 should be equals to magnitude of E2 E1 k q1 is 16 microcoulomb divided by L plus x whole square. Here L is 8 centimeter. 8 plus x whole square must be equals to magnitude of electric field intensity E2 due to minus q2 k, magnitude of charge 9 microcoulomb divided by square of distance is x square, k microcoulomb, then 16 divided by 8 plus x whole square is equal to 9 divided by x square. Now taking square root on both sides, 4 divided by 8 plus x is equal to 3 divided by x, cross multiplying, 4x is equal to 24 plus 3x, then 4x minus x is x is equal to 24 centimeter. Okay, thus at a distance 24 centimeter from smaller charge, we will have zero resultant field intensity due to these 2 point charges. Okay, finding easier. Okay. Then question number 4. Question number 4, again we are approaching easier questions. Question number 4. 2 point charges. See students, I will now take variables. I will not use numerical values. Okay, if numerical values will be given to you, you can just put your values. Okay, so another okay, ठीक. 2 point charges each of plus q are placed at the vertices of an equilateral triangle. These are very common questions. Okay, equilateral triangle upside A or L, whatever you may take. Okay, find electric field at the third vertices. 2 point charges each of plus q. Okay, in place of plus q, any value of charge could be given. This is an equilateral triangle. Let's consider an equilateral triangle. Each side of the triangle is A. At the 2 vertices, there are 2 point charges plus q and plus q, and we have to find resultant electric field, means sum of electric field due to 2 charges at the third vertices. Okay. So this is the point where we have to find resultant field intensity. Again, as per principle, where we have to find electric field intensity, we have to place on unit positive charge at that point. Then magnitude and direction of field intensity is same as that of force experienced by the unit positive charge. This plus q will repel it. Let intensity is u1 and magnitude of u1 is k q divided by square of distance. This plus q will also repel it. Let intensity is E2. Again magnitude is kq divided by square of distance. Magnitude of charges are same. Also distance from the charges to this required point is same. That's what we got. Magnitude of E1 is equal to magnitude of E2. So there are 2 field intensity at this point due to 2 point charges, and we have to add these 2 field intensities so as to get resultant field intensity. Okay, I am bringing the diagram here, vector diagram. This is direction of E2, this is direction of E1. Okay, since it's an equilateral triangle, this angle is 60 degree. Also this angle is theta, means 60 degree. So I may take this angle is theta, means 60 degree. Now 2 vectors, E1 vector and E2 vector are 2 field intensities are impressed at this point. To get resultant field intensity, let's follow parallelogram law of vector addition. Now let's complete parallelogram. Okay, these 2 vectors are components. As per parallelogram law of vector addition, if 2 vectors can be represented in magnitude and direction by the 2 adjacent sides of a parallelogram, then diagonal of the parallelogram passing through the intersection of the vectors represents magnitude and direction of resultant field intensity. Here, resultant electric field intensity is sum of field intensities due to these two charges, and angle between them is theta. So let's find first resulting magnitude of resultant field intensity, square root of E1 square plus E2 square plus E1 E2 cos theta is 60 degree. Since magnitude of E1 is equal to magnitude of E2, we may write E1 square plus E1 square means 2E1 square plus 2E1 into E1 again 2E1 square cos 60 is 1 by 2. Okay. We are taking E1 is equal to E2 is equal to E1. In place of E2, E1 square plus E1 square 2E1 square, again 2E1 into E1 is 2E1 square. 2 get cancelled, then this is equal to square root of 3E1 square. So this is root 3E1. So magnitude of resultant field intensity is root 3E1, and since E1 or E2 is kq by r square, this is magnitude of resultant field intensity. You may show here, this is resultant field intensity and this is direction. Direction is let alpha, obviously it will be 30 degree. According to principle of vector addition, if magnitude of two vectors same, then the resultant must bisect the angle between the vectors. Here resultant bisects the angle 60 degree, means direction of resultant is 30 degree with any of the vector, means either with E1 or with E2. Okay. Then I am changing this question number 5 a little bit. 2 point charges, each of plus q, 2 point charges of plus q and minus q. One is positive, other is negative, are at the vertices of an equilateral triangle of side A. Find resultant field intensity at the third vertices. Okay. Suppose these are the two charges, this is positive and this is negative. We have to find resultant field intensity or the third one. Let's place on unit positive charge. We have already discussed the concepts. Then plus q will repel it. Let field intensity is E1. Minus q will attract it. Let field intensity is E2. Again, magnitude of E1, magnitude of charge is same q and q, also distances are same a and a. Thus magnitude of E1 is equal to magnitude of E2, that's equals to kq by a square. Then we have to get resultant field intensity due to sum of two field intensities E1 and E2, and angle between them is, let theta is equal to 120 degree. The total angle is 180 degree and this is 60 degree. Now again, let's follow parallelogram law. Okay. These are two vectors represented in magnitude and direction by the two adjacent sides of the parallelogram. This diagonal represents resultant field intensity. Okay. Here magnitude of E1 is equal to magnitude of E2. So directly magnitude of resultant field intensity will also be equals to E1 or E2, either of them. Okay. This is the concept. If two vectors have same magnitude and angle between them is 120 degree, then magnitude of resultant will also be equals to magnitude of either of them. Okay, you know it. Thus magnitude of field intensity, square root of A1 square plus E2 square plus 2E1 E2. Theta is 120 degree cos 120. Again, magnitude of E1 is equal to magnitude of E2. E1 square in place of E2 square, we can write E1 square plus 2. E1 in place of E2, E1, 2E1 square cos 120 degrees minus 1 by 2, and we will get square root of 2E1 square minus 1 by 2 get cancelled, minus E1 square. Okay. Then finally magnitude of resultant field intensity is square root of E1 square means magnitude of E1, that's equals to KQ by A square. Again, the resultant will bisect the angle because here magnitude of E1 is equal to magnitude of E2. Thus, the resultant must bisect the angle between the two component vectors. Okay. Then, question number 6. Another similar type of question. These are regular questions. Okay. 2 regular questions and most common questions. In next lecture, we will try to attempt some numericals which will be applicable for your competitive exam. In lecture 10, we will try to attempt, we will approach, okay. In lecture 10, we will approach some numericals. Some of them will be very important for your competitive exams like NEET and JEE, etc. Okay. The next question. Question number 6. 3-point charges. 3-point charges, each of plus Q, or you may change the sign of any of the charge. Okay, only direction of forces or direction of electric field intensity will be different. Each of plus Q are placed at the corners of a square upside A. Okay. Find resultant field intensity at the remaining corner. All these questions comes under the principle of superposition effect of electric field intensity, as we have discussed. Superposition effect of Coulomb's law. Okay. Let's consider this is a square. Okay. These are 3 corners. At one corner plus Q, next corner plus Q, next corner also plus Q. Side of the square is A. We have to find resultant field intensity at the remaining corner, means we have to take vector sum of field intensities at this point due to 3-point charges. Okay, only superposition effect. Then this plus Q, where we have to find electric field, we have to place an unit positive charge. As we have discussed, electric field is force experienced by unit positive charge or force divided by unit positive charge. Okay, this plus Q will repel it. Let field intensity is E1 and magnitude of E1 is KQ divided by square of distance. Also this will repel it. Let intensity is E2, again magnitude is KQ divided by square of distance. Thus what we got, magnitude of E1 is equal to magnitude of E2. Then obviously angle between them is 90 degree. Let's complete the parallelogram. Okay. Then magnitude of E1 is equal to magnitude of E2. What we have discussed, if magnitude of 2 vectors is same, then the resultant must bisect the angle between the vectors. So this is the resultant. Let this resultant is E3. Means E3 vector is equal to sum of E1 vector and E2 vector. Then magnitude of E3, we are adding E1 and E2. Then magnitude of E3 is square root of E1 square plus E2 square plus 2 E1 E2 cos theta is 90 degree, and magnitude of E3 square root of E1 square plus E2 square. Since magnitude of E1 is equal to magnitude of E2, we can write either square root of 2E1 square or square root of 2E2 square. In place of E2 we may take E1, or in place of E1 we may take E2. Then magnitude of resultant field intensity is root 2 E1 means root 2 E1 or E2 KQ divided by square of distance. So this is resultant field intensity due to these 2-point charges. Then what about 3rd-point charge? This will also repel it. Let intensity due to this plus Q at this point is E4. Resultant of E1 and E2 is E3 and field intensity is E4 due to the remaining charge. Then magnitude of E4, K, Q, this distance, this is A, this is A, this is 90 degrees, so obviously this distance is root 2A. Divided by square of distance, square of root 2A means 2A square. See students, E4 field intensity due to this charge E4 and resultant field intensity due to E1 and E2 is E3. E3 and E4 are in same direction, thus final resultant field intensity. Resultant electric field intensity. Magnitude of resultant field intensity must be equals to magnitude of E3 plus magnitude of E4 since angle between E3 and E4 is 0 degree. Again, direction of resultant field intensity will be along the direction of E3 or E4. Okay. Then resultant field intensity, magnitude of resultant field intensity E3, we have got E3 means root 2 KQ by A square plus E4, we have got E4 KQ divided by 2A square. Now I will solve it to get your final answer. It is easier one. Then magnitude of resultant field intensity KQ divided by A square root 2 plus 1 by 2 and the electric field intensity K 1 divided by 4 pi epsilon naught Q by A square into 2 root 2 plus 1 divided by 2, then final answer 1 divided by 2 into 4 8 5 epsilon 0 Q by A square into 2 root 2 plus 1. Okay, very easy question. Then next question, I think question number 7. Question number 7. In Millikan's oil drop experiment, in Millikan's oil drop experiment, an oil drop of mass. See students, in Millikan oil drop experiment, an oil drop is released in space, but it neither falls down or rises up under the effect of electric field because the oil drop is charged. Okay, I am writing the question. In Millikan's oil drop experiment, an oil drop of mass 10 to the power minus 7 kg is held stationary in space so that it neither rises nor falls. Okay, if the oil drop has one excess electron, find magnitude and direction of electric field intensity. Required to keep the oil drop in equilibrium. An oil drop, in Millikan's oil drop experiment, an oil drop of mass 10 to the power minus 7 kg is held stationary in space. This is space. If I hold an oil drop and release, then it will obviously fall down. Why it will fall down? Because weight of the oil drop acts in vertically downward direction. The weight imparts a force on it in vertically downward direction, so it will fall. But it doesn't fall. Okay. Is held stationary, kept at rest in space, so that it neither rises nor falls. If the oil drop has excess electron, one excess electron, then charge of oil drop, as you know, charge is equal to Ne. N is number of free electrons or number of electrons excess or deficit of electrons maybe. So here the oil drop has excess electron, means one excess electron. So N is 1, charge is G. Obviously, due to excess electron, charge of oil drop is negative, minus Q. So Q is equal to minus C. Okay. One excess electron, find magnitude and direction of electric field intensity required to keep the oil drop in equilibrium. See, the weight of oil drop tends to bring the oil drop to the surface of earth. So to balance the weight, there must be an upward force, means opposite to the direction of weight. Okay. How the oil drop experience an upward force? Oil drop has negative charge, minus Q. Then this charge means this oil drop should be attracted in opposite direction. Okay. To attract negative charge, positive charge is required. Okay. Just imagine this is a metallic plate. This plate is positively charged. Okay. Let's imagine this is another metallic plate. This metallic plate is negatively charged. Then in the space between the two plates, there will be an electric field, means uniform electric field, which is directed in vertically downward direction. So, direction of electric field is from positive to negative. Electric field lines start from positive and end on the surface of negative charge body. So, in potential, we will change our view to a new form. Means the direction of electric field is from high potential to low potential. High potential we mean positive, low potential we mean negative. So this is the direction of electric field. Thus the negatively charged oil drop experiences an attracting force in upward direction due to positive and a repelling force in upward direction due to negative. Thus resultant force experienced by the oil drop is in vertically upward direction and weight of the oil drop in vertically downward direction. So both are in opposite direction. So these two forces should have equal magnitude so as to keep the oil drop in equilibrium. So here upward force plus weight of the oil drop should be 0. Means sum of these two vectors is a null vector. So we may say magnitude of force must be equals to magnitude of oil drop. These are opposite in direction. Only condition for equilibrium is they are same in magnitude. Force is QE. Weight here Q is charge due to a single electron into magnitude of electric field is equal to mg, and it is required to find magnitude of field intensity, which is equals to mg divided by charge of electron, and mass of oil drop is given 10 to the power minus 7 kg g. We may take 10 meter per second square. Charge of electron 1.6 into 10 to the power minus 19 coulomb, and solving it we will get magnitude of electric field intensity 6.125 into 10 to the power 12 Newton per coulomb, and direction is vertically downward. Okay. If the oil drop were positively charged, Here oil drop is negatively charged, so direction of electric field should be in vertically downward direction. If the oil drop were positively charged, then electric field should be in vertically upward direction. If this charge were positive, then this should be positive, this should be negative. Positive will repel positive in upward direction, and this negative will attract the positive charge in upward direction. This is basic concept. Okay. Then question number 8, I am changing this question. In Millikan's oil drop experiment, an oil drop, suppose mass is not given. An oil drop of radius, no, suppose radius is asked, let oil drop has charge, oil drop has 6 excess electrons, is held stationary in space so that it neither rises nor falls under an uniform electric field, under an uniform electric field of 25.5 kilovolt per meter. 25.5 kilovolt per meter. The oil drop, no, this line is not required now. Okay. 25.5 kilovolt per meter. Okay. If density of oil, density oil drop means density of oil is, I am taking density of oil is 1.26 into 10 to the power 3 kg per meter cube. Find radius of the oil drop. Again, the oil drop has 6 excess electron. Again, charge is negative, means this charge is minus 6e. Due to excess of electron, charge is minus 6e. Mass is not given. Again, the same concept, electric field, direction of electric field should be in vertically downward direction, and force due to electric field must balance weight of the oil drop. Then force plus mg is equal to 0, force is equal to mg, QE is equal to mg. So far this is right. Okay, I am erasing this. Then charge, here charge is 6e, total charge Q is equal to 6e. Then 6 E into E is equal to mass of oil drop. Since density of oil drop is given and radius of oil drop is asked, then mass is density into volume. Volume of oil drop, spherical oil drop 4 by 3 pi r cube, mass density into volume into G. Okay, 4 by 3 pi r cube is equal to 6 E divided by rho G. I will erase this now. Then R cube is equal to 6 E divided by 4 by 3 pi rho G. Okay. Then R cube is equal to 6, charge of electron 1.6 into 10 to the power minus 19 coulomb, and electric field. See students, units of electric field is given 25.5 kilovolt per meter. What we have discussed in potential, electric potential, we will know another new system of units for electric field. Units of electric field may be Newton per coulomb or volt per meter. Here magnitude of electric field is given kilovolt per meter. So 25.5 into 10 to the power 3 kilovolt is converted to volt per meter. Then in place of electric field we may write 25.5 into 10 to the power 3. Then 4 by 3 pi 22 by 7. Density of oil drop 1.26 into 10 to the power 3 kg per meter cube, and G we may take 10, and solving we will get radius is equal to 4.3 into 10 to the power minus 7 meter. Okay, this is our answer. Okay, so this is about lecture 10. We have discussed some of two fundamental, very easy and fundamental level numericals on electric field. Okay, in next lecture, means in lecture 10, we will again discuss some important numericals based on electric field. Don't miss lecture 10. Carry on. Thank you.